uh, stopped somewhere at the beginning of this lecture 2. So we will try to complete that and also continue with lecture 3. So we talked a little bit about Mohr circle, so you can represent the stress states in any kind of any material or component in terms of tension, torsion, etc. So if you have a tensile load, the first one you represent that as um, a tensile load that is on the positive side, but you also have a shear load that is happening at the same time, which is equal to 1/2 of the tensile load. That is a maximum for this material. If you have a component under torsion, that means this is represented as you will know, the stress is equal to the uh, the uh, the torsional stress also. That both are equal. Okay, so and if you have triaxial tension where the component is being pulled equally in all directions, um, that means the tau max over sigma max is approaching 0. And if you have compression, hydrostatic compression, like in the case of an autoclave or something like that, it is negative. So which means it is placed on the negative side on the Mohr circle. So you know that, and you know we also talked a little bit about toughness of how do you represent the toughness of materials. So what is toughness? We try to represent that as the area under the stress strain curve. So if you have a component that is having a stress strain curve like this curve C, that has a higher toughness than either uh, B or A, and these are mostly metallic materials. So if it is a ceramic, you will probably have um, a stress strain curve that is equivalent to A, and if you have um, a rubber type of a material, you will have a stress strain curve that is equal to B. So these are some of the equations that you might be finding. I think these equations might be slightly different in uh, in uh, the uh, the fifth edition of Hertzberg. So these equations are probably coming from um, edition 4, but you will probably find the equations for all that in the edition 5 also. Okay, so and talking in particular about rubber type of materials, you have um, these materials. Suppose you apply a load, um, it will start showing uniform um stress strain behavior in the second stage, and then after that it starts taking up all the way to the up. But if you release that load, it is going to release in this manner, and it is a non-linear fully reversible strain, but elastic modulus actually increases with temperature, which is opposite to that of metals, and especially because when you heat it up, it becomes more crystalline, so that becomes more brittle and therefore higher elastic modulus. Okay, and um, I want to generally talk a little bit about composite materials. Why do we want to talk about composite materials? Composite materials are some of the most interesting materials ever discovered, and because you are bringing together uh, two different materials that are entirely different from each other, and then you get a property that is somewhat in between the two types of materials. And you can have a matrix that is either ductile, like metals or polymers, and the reinforcement, which would be either glass, ceramic fibers, or particles, or uh, or Kevlar type of fibers. And it is used quite extensively in the aerospace industry. Now it is being used in the automotive industry. Um, it is also used in the wind turbine industry, like RV industry, etc. So, because they are anisotropic in different directions, so you don't have the same properties in all different directions, like in the case of metals. So, uh, if you if you know the constituent properties, if you know the constituent materials and their properties, you can actually predict the behavior of these materials. So it makes it very easy for you to use them in your design type of application. So you can design components based on that, even though they are anisotropic. You can take that into account and uh, use it to predict the properties. And for that, you need to know the relative percentage of the matrix and the reinforcement material. And there are two ways to do this analysis. One is, it's called isostrain, and the second one is isostress. Isostrain means you have the same strain that is taking place in the entire material. It is the same in the fiber, which is subscript F, and the matrix, which is subscript M. So this is the analysis of that, but don't get too caught up in this derivation. But what I want you to pay attention to is this, that is, the elastic stiffness of the composite is a weighted average of the elastic stiffness of the fibers times the volume fraction of the fibers plus the elastic modulus of the matrix times the volume fraction of the matrix. So, which means that if you know the constituent properties of these materials, which you can get from any handbook nowadays, you can actually calculate the stiffness of the composite itself. Now, are you going to get 100% of this? Probably not, but this gives you the upper bound of the properties that you will get by bringing together two different types of materials together. Now, you can have both the fiber and the matrix that are elastic and your properties are going to be somewhat in between. The composite properties are going to be somewhat in between the fiber and the matrix. The matrix is slightly ductile after a certain stage, or not ductile. I mean, it's plastic after a certain stage. So it is linear only up to a certain stage, up to the fiber um, failure strain, but beyond that, it starts acting in a plastic manner. You can also have some amount of plastic deformation in the um, in the matrix, much more than the fiber. So, which means that the composite also will start showing some amount of plastic deformation beyond a certain stage. So this is how the stress strain behavior of a composite will look like. Most of the time you are probably going to find this, or you might find somewhat in between the two types of behaviors. So you can actually predict the behavior of these materials in this manner. So if you take the individual constituents, you can actually calculate the properties of the composite materials. So you can see the if you have a polyester resin, which is typically used in boats and things like that, and if you have aligned glass fibers, you can see that it has an elastic modulus of 38 gigapascals, or 5.5 ksi, or 5.5 msi. I'm sorry, 5.5 msi. And you can see that the tensile strength is about 110 ksi. But if we have random orientation of the fibers, then the same material combination will show you much lesser properties than the aligned fibers. So you can see the effect of the alignment of the fibers here. Okay, and the same thing um, with viscous reinforcement, or with carbon fibers and etc. And these are the individual reinforcement properties. So you can see that they are very high in strength, but when you add them to a ductile matrix like epoxy, or a ductile matrix like a metal, you can see how the properties change as a result of adding these uh, adding these fiber reinforcements. So if all the fibers are aligned in the direction um, of the loading, you can see that the elastic modulus of the composite material increases monotonically from the um, from the property of just the matrix where you don't have any fiber reinforcement at all, to 100% fibers. So which means it'll be that high. So if you can see that it'll be somewhere in between. But if you had fibers that were perpendicular to the loading direction, they do not increase the elastic modulus of the composite the same manner. I mean, so they would increase gradually and only go up to a certain extent. Whereas if the fibers themselves, they will have as high as um, about 10, 12 MSI. You can see that the composite, if the fibers were all aligned perpendicular uh, to the uh, to the loading direction, you can see that the elastic modulus does not go beyond about 5 MSI. So in order to get full benefit of the fiber reinforcement, you have to have more fibers aligned in the orientation of the normal loading direction, or close to the normal loading direction. So you can see that there is a critical volume fraction of the fibers that are required in order to get the benefit of the fiber reinforcement. And in the case of polymer composites, it is approximately 60 volume percent fibers, whereas in the case of ceramic composites, it is approximately 40% fibers. So you need approximately that much in order to get the benefit of the uh, reinforcement of the matrix. And if they are not aligned, entirely aligned, to the normal loading direction, you can actually calculate the the values of the properties of the composite in different directions and combine all of them together in order to get the elastic modulus of the composite itself. So you can also see that there is an effect of fiber orientation on the composite strength. So if the angles are different, they can have some benefit, but they don't always benefit completely. So which means that if you have somewhat between 50 and 60% uh, fiber volume fiber volume in the composite, that is the best, and the matrix is just there to hold the fibers together. In the case of isostress, that condition is where the load is equal in the composite, the fiber, and the matrix. So which means all the fibers are oriented in the perpendicular to the direction of the loading. That is called the isostress condition. So in this case, you can see that the composite elastic modulus is slightly less than what was predicted by the first case, which was the isostrain condition. Okay, where the failure strains were equal, the strains were equal in all the three components together, all the three constituent materials. But in this case, you are considering that the load is the same. And what you will see is that um, the isostress gives you the lower bound of the properties that you will get in the case of composite, whereas the isostrain would give you the upper bound. And I will post you some sample problems. You may have done this in the ENSC 3313 class. So I would suggest that you go back and look them up again so that you get familiarized with the analysis and how to calculate the individual constituent properties. Okay, so um, coming to the next portion of this lecture, uh, we want to see how pressure vessels have to be designed and what the wall thickness does. How do you calculate the wall thickness and how do you calculate the stresses, etc. So I'm not going to go over the derivation of these equations, but essentially you can see that the uh, the tangential or on hoop stress on a pressure vessel or a pipe is given by sigma is equal to the load times the diameter divided by twice the thickness of the wall. Whereas in the case of the longitudinal stress, there is a stress in the longitudinal direction or the flow direction, you can see that it is half of that of the hoop stress. So, and we will be discussing more about this when we talk about things like uh, stress intensity factors, etc. So you can use these equations to calculate. So if you know the material, you can calculate the wall thickness that is required for a pipe made out of that material. Okay, and I think we talked a little bit about the uh, effect of strain rate behavior and the temperature effect. Okay, you can see that I think I mean this is repetition of what we had talked about in the ENSA 3313 classes. Okay, so if you have a material, say for example a metal, it behaves in a plastic or heterogeneous manner when you apply a load. So if you plot the stress versus strain, this is how it looks like, T3. And if you increase the temperature, you know that the elastic modulus will start decreasing and it will become more plastic. And if you increase the temperature even further, it decreases even further compared to the either of the first two cases. So you can see that T1 is greater than T2 and greater than T3. So you can see that if you increase the temperature, the stress strain behavior becomes more plastic, for especially in the case of metals. And another factor to consider is strain rate. So the rate at which you strain or stress the material is going to be controlling the stress strain behavior of the material. Okay, so you can see that if you increase the straining rate, the material actually becomes more, it becomes stronger, but it becomes more brittle. So you can see that you can actually plot um, and say that sigma is equal to k times epsilon dot, which is a strain rate, which is the strain per over time, incremental strain over time to the power m, where m is a strain rate sensitivity factor. So you can look at some sample problems and I will also post them. You can use that too. So you will find similar problems uh, in the homework sets. Okay, so where does all this come into play? I mean, it comes into play when we are talking about how do you predict the failure of materials. So the first theory of failure prediction is called the Tresca criterion. So what does that tell you? It tells you that yielding occurs when the maximum shear stress reaches shear stress in a uniaxial tension test. So and in the case, I mean, the standard format for the shear stress is equal to sigma 1 minus sigma 3 divided by 2, where sigma 1 is a normal load, sigma 2 is the load in direction 2, and sigma 3 um, is the shear stress. No, not shear stress. I mean in direction 3. So if you have if you know the three stresses, you can actually calculate the tau max. And you know that for uniaxial tension, um, sigma 1 is equal to the applied stress, whereas sigma 2 and sigma 3 are supposed to be equal to 0. And so if you know the shear strength of the material, if you if your normal stress becomes equal to half the shear strength, then the material will start yielding. So sigma 1 and sigma 3 are the maximum and minimum principal stresses. So you will be given these values and you will be asked to calculate those things. And the next one is called the von Mises criteria, which is slightly more complicated than the Tresca criteria. So in this case, if you know the stresses in the sigma x, sigma y, and the sigma c conditions, this is given by this equation. And if you if you know the sum of them and if the others are equal to 0, then uh, if this value exceeds the uniaxial yield stress, uh, that means this will this material will start yielding. So that's what you include in your design in order to do that. So these are two examples. So if you are given these values, okay, sigma x, sigma y, and sigma c, and you have tau xy, so you are given these values. So according to the von Mises criteria, uh, sigma 0 equal to 500 megapascals. So both the von Mises criteria and the Tresca criteria predicts that there is no yielding. So the von Mises criteria is a little bit more accurate than the Tresca criteria. I think this one comes from a previous. I think we talked about that in the last class. So I will not go over that. So if you are given these values, so you can use that to calculate the yield criteria for according to von Mises or Tresca. Okay. So if you are given these values, so you will be asked to calculate something based on that. So these are again coming from the textbook. I'm not going to go over that. Um, so you will be asked to calculate the yield phenomenon or whether yielding will take place or not in a material based on these values according to either the Tresca criterion or the von Mises criterion. Now, let us go over dislocations. What are dislocations? Dislocations are the phenomenon that is causing a material to deform. So the yielding also takes place as a result of dislocations. So if you know that dislocations are moving, that means the yielding is taking place in a material. So what are the different kinds of dislocations that you know of? Edge dislocation and screw dislocation. I hope you will go back to your ENSE 3313 and brush up your knowledge about dislocations. So what are dislocations actually moving? Dislocations are what causes deformation, and in this case it can be either permanent or temporary. Temporary deformation is elastic deformation. Permanent deformation is plastic deformation. So what do we assume? We assume that most of the time the crystal lattice is perfect, and in order for a material to deform plastically, you have to break those bonds and you have to make those dislocations start moving from one point to the other. So for example, if you have two blocks of material and those there are bonds between the atoms, the different bonds are there, and what does it do? So you are applying a force in order to move those bonds Um, so you can actually move from the point, I mean the atom from this point to this point. Okay. Now, if the force is not large enough, they will come back to this position. But if the force is too much and it allows those bonds to be broken, then they will move from this point to over the next one. Okay. So I'm not going to go over the derivation. So for a material to deform plastically, you need a certain amount of shear stress. So in order for these atoms to be moved from this point to this point, you need to shear them. And for that, you need a shear stress to be applied. And that shear stress theoretically can be calculated to be equal to G, which is the shear modulus of the material, over 2 pi. It is an approximation, but that is what it is. So they can, I mean, and it is also equal to B, which is the Burgers vector of the material, which would be how much movement has to be made for moving the dislocation from one point to another, and A is the lattice constant. Okay, but they can be approximately equal, made equal to G over 2 pi, which would be G is the shear modulus over 2 pi. Okay, and you can see that this is the theoretical value for different materials. So for example, for silver, it is 4.6 gigapascals, or um, it is approximately 0.67 MSI. But you can see that if you experimentally calculate that, the shear, um, shear stress value in order for you to move those atoms is much less than what is theoretically predicted. So for example, if you have say copper, it is 7.2 gigapascals, but experimentally it is only 0.49 megapascals. Where is zero point 0.4, half a megapascal, and where is 7.2 gigapascals? They are completely, I mean, they are much lower than this value. And we will learn what exactly is happening that is causing this reduction experimentally compared to the theoretical value. So there is a large discrepancy between the theoretical and experimental strength of materials. So the mechanism of plastic deformation is somewhat different than just simultaneous bond breakage. Okay, and that is because of the presence of defects, which are dislocations. So you know that in the case of the edge dislocation, it is an extra half plane of atoms, which is this extra half plane of atoms. So you are moving those dislocations from one, I mean, so suppose you are shearing this top block of atoms over the bottom block of atoms. So you are breaking these bonds, those atoms just comes to the uh, next um, equilibrium point, and then so on. So afterwards, this completely moves from one point to the other. Okay. So, and it is, please take it as a given, the lower experimental strength in real materials is due to the consecutive bond breakage as opposed to simultaneous bond breakage in perfect crystals. So you can think of this as, like, think of this as a carpet. I mean, something in a carpet. Okay, so you're moving that from one point to the other. So if you want to move this hump in the carpet from one corner to the other, how would you do that? So it is similar to moving these atoms from one point to the other. Okay, so you just roll that slowly. I mean, suppose you have to take the carpet and pull it from one side to the other, you will require much more force in order to do that. But if you move this uh, half a um, point, I mean, like, one layer at a time, you will require much less stress in order to do that. So once you do that, then you have completely removed this hump from one point to another. And that's how atoms move in the case of real crystals. So this is given by what is called the Peirce stress, and that can be that has been theoretically calculated to be equal to uh, given by this. I mean, this is the stress that is required uh, in order to move the one dislocation through the lattice from one point to another. Okay, so in this case, suppose this is the width of that dislocation, and suppose this is the area where the dislocation is there, and if you know that, where nu is the Poisson's ratio of the material, and b is a Burgers vector um, of the dislocation, so which you can actually see get from handbooks and things like that. So I mean, even in your textbook, you should find them for different types of materials. So if you know the extent to which the lattice is distorted and the distance between the planes, then you can actually calculate um, the force that is required in order to move the dislocation through that lattice. So you can see that in the case of FCC type of materials, you can see that the Peirce stress is very small. In the case of BCC, it is slightly moderate. So if you have a ceramic, you can see that the crystal type is covalent, which means that the Peirce stress is extremely large. So that's why you require a lot of force in order to elongate a ceramic type of covalent ceramic type of material. But an FCC material, what are some examples? Aluminum, copper, etc., or steel at elevated temperatures. You can see that they will start moving very easily as a result of the Peirce stress, as a result of application of the stress. So the Peirce stress, if you calculate that theoretically, you can see that it is much less in the case of FCC compared to BCC or ceramic type of materials. So here again, I mean, this was what uh, so suppose you had uh, a material where there were no dislocations at all. You can say that theoretically it should be this high, but experimentally it is much lower than that. So you will see that there is some um, effect of defects that you are introducing into the material. So And you probably remember this, that there are two types of dislocations, which are edge and screw. Um, and In the case of edge dislocations, they can be either positive or negative. Um, so this is a positive type of edge dislocation, and there is another factor that is associated with dislocations, which is called the Burgers vector, and it represents the distance that you need to travel in order to complete the cycle if the dislocation were not present. So in this case, so this is the Burgers vector B equal to, and the moment of dislocations in the case of materials, I mean especially metals, is called slip. You are slipping the material one on top of another. So that is, and it happens in the case of close packed planes, which are the ones with the greatest atomic spacing. So these would be the greatest atomic spacing. And does that happen? Because you need the least amount of force that is required in order to move those atom blocks of atoms. So we saw this picture in an earlier image. So you can see that in order to move this block from one side to another, you need to apply a force, and that force is called, theoretical force is called Pearl's stress. So you can also have, suppose you heat up this material, you can also have those edge dislocations move from one location to another in the lattice. So in this case, you're only moving it in one direction, which is kind of perpendicular to the direction of the, or parallel to the direction of the force. But in this case, if you apply a heat or temperature to this material, that dislocation can move from one location to another just by the diffusion of the atoms. So the diffusion of the atoms is helped by the application of temperature. So they can just move from one location to another. So that is another way for the material to deform. So you can see how that correlates to materials that are heated and deformed to other shapes, smaller shapes and things like that. Say for example, if you are drawing a wire from a thick diameter to a smaller diameter. You can also have what are called screw dislocations. So they are kind of different from the edge dislocations, but they are um, not exactly in the plane of the atoms. They are kind of in a dip or valley. I mean, so you have sheared the plane of atoms one on top of another, like if you like opening up a bottle. Okay, so you are displacing one part of the crystal relative to the other, and the Burger circuit is in the form of a helix. So in this case, I mean, again, B, which is a Burgers vector, is parallel to the slip direction, and it is parallel to the dislocation line. So there are no unique planes for screw dislocations, and so they have greater mobility than an edge dislocation. But the reality is that dislocations are neither edge nor screw. They have a property that is somewhat in between. There is some edge features to a dislocation, and there are some screw features to a dislocation. So they would move differently, but they move nonetheless. Okay, so screw dislocations, how do they move? So they, I mean, the first one, the most easiest one is to um, just move them as a result of um, just application of the shear motion on the plane of atoms. And the non-conservative motion, which would be they would just move from one plane to another by the application of temperature. So in the case of the edge dislocation, um, you can either shear the plane of atoms one on top of another. That would be the simplest case, and the second one would be the case where you apply heat, which would make the atoms diffuse from one location to another and cause the edge dislocation to move. And in the case of the screw dislocation, you can shear them, and then you can also um, apply a temperature and cause the atoms to move from one plane to another, which would be called cross slip. So let me stop here, and I will continue the next lecture in another video.